Welcome to our Quantum Deep Dive. Today, we're jumping into one of the biggest, most mind-bending puzzles in all of science. And we're doing it based on an incredible essay by Jürg Oesch-Schneppert. It's a story all about a riddle that so deeply bothered Albert Einstein, it made him question the very fabric of reality.
And it all kicks off with this one famous, almost notorious phrase from Albert Einstein himself, spooky action at a distance. Now, this wasn't just some throwaway comment. This was a deep, fundamental problem that one of the greatest minds in history had with the new, bizarre rules of the quantum world.
So here's how we're going to break it all down. First, we'll get into what exactly Einstein's spooky problem was. Then, we'll dive into the huge debate it started. After that, we'll see how scientists finally put reality on trial, what the astonishing results were, and finally, how we're now actually using that spookiness to build the future.
All right, let's get right into it. What was this phenomenon that bothered Einstein so much? At its core, it's an idea that just seems to completely break our everyday understanding of how the universe is supposed to work.
Okay, so the concept at the absolute heart of all this is something called quantum entanglement. Picture this. Two particles are born together, and from that moment on, they're linked. They are now one single system. And it doesn't matter how far apart they get, across a lab or across the entire universe, what happens to one instantly affects the other. Now, your first thought might be, okay, so what? It's like having a pair of gloves. If you open a box and find the left-hand glove, you know the other one is the right-hand glove. Simple. But here's where it gets really spooky, and this is the part that drove Einstein crazy. According to quantum mechanics, the particle doesn't have a definite state until you look. It's in a fuzzy cloud of possibilities. The moment you measure one and it decides to be heads, the other one, even if it's light years away, instantly becomes tails. To Einstein, that was impossible. That was spooky action at a distance. So you can probably imagine this idea of an instantaneous, faster-than-light connection. It didn't just go unnoticed. It kicked off one of the biggest intellectual battles of the 20th century. This wasn't just about formulas. It was a fight over what reality even is. So back in 1935, Einstein got together with his colleagues, Boris Podolsky and Nathan Rosen, and they dropped a bombshell paper. The title alone says it all. Can quantum mechanical description of physical reality be considered complete? Spoiler alert, their answer was a big no. They argued the theory must be missing something, some hidden variables that predetermine the results, so there's no spooky communication needed. This all boils down to two completely different ways of looking at the universe. On one side, you have Einstein's local realism. It's based on two ideas that just feel right. One, stuff has definite properties whether we look or not. The moon is still there when you close your eyes. And two, locality. Nothing can go faster than light. But then you have quantum mechanics, which throws that rulebook out the window. It says properties are fuzzy probabilities until you measure them. And entanglement creates these non-local connections that seem to break that ultimate speed limit.
So, which is it? For decades, this was just a debate. A really smart debate between giants like Einstein and Niels Bohr, but a debate nonetheless. It felt purely philosophical. I mean, how could you ever build an experiment to test the fundamental nature of reality itself? But then, things changed. The whole argument just sat there for years until the 1960s. That's when a physicist named John Stuart Bell came along and did something absolutely brilliant. He found a way to take this argument out of the philosophy department and put it into a real-world lab. What Bell did was genius. He turned this philosophical fight into a testable prediction. He created a theorem that set up a clear contest. He proved that if Einstein was right, if there were hidden local instructions, then the correlations between measurements on these particles could never, ever exceed a certain limit. This became known as Bell's inequality. But if quantum mechanics was right, the correlations would be stronger and would break that limit. And that led to these incredible experiments, with pioneers like Alain Aspect leading the charge in 1982. The setup was so clever. You create these pairs of entangled photons, and you shoot them off in opposite directions toward detectors. At each detector, you measure a property, like its polarization angle. And this is key. You choose the angle randomly at the last second. Then you do this thousands of times and compare the results to see just how correlated they are. All right, so after all those decades of arguing, the stage was finally set. It was time to just ask the universe itself for the answer. And let me tell you, the answer it gave back was a total game changer, and it shook physics to its core.
So Bell's theorem drew a clear line in the sand. If Einstein's view of a nice, orderly, local universe was correct, the statistical score for the correlations could never go above the number 2, ever. But if the quantum world was truly spooky and non-local, the correlation would be stronger, breaking past that limit. The whole thing came down to this: what would the number be?
And the results were just wow. Experiment after experiment, they ran the numbers, and every single time the limit was broken. The correlation wasn't 2 or less, it was way higher, landing almost exactly where quantum theory predicted it would be. The universe had spoken, and it sided with spooky.
So there it was. The verdict was in. Reality is non-local. The universe is, in fact, spooky. Einstein's powerful intuition, which had been so right about so many other things, just happened to be wrong on this one. These strange instantaneous links aren't a bug in the theory, they're a core feature of how our universe actually works. And this is where the story gets really, really cool. Because what started out as this deep philosophical puzzle is now the engine driving a whole new technological revolution. That very spookiness that Einstein couldn't stand, we're now building the future with it.
Take communication, for example. Entanglement makes truly unhackable cryptography possible. Imagine you and I share a secret key using entangled particles. Because that link is so delicate, if anyone tries to eavesdrop, to just peek at the particles, they instantly break the entanglement. We'd know immediately that someone's listening. It's security that's literally baked into the laws of physics.
And then there's computing. Oh man, entanglement is the secret sauce for quantum computers. They use these things called qubits, which, thanks to entanglement, can explore a huge number of possibilities all at once. This lets them tackle certain problems, like breaking today's encryption, that would take the fastest supercomputers we have now literally billions of years to solve.
It's even changing how we measure things. By using entangled particles, we can build sensors that are ridiculously precise, way beyond anything we could do before. We're talking about next-generation atomic clocks, detectors that can feel the tiniest ripples in space-time from gravitational waves, and even advanced medical imaging, all powered by these spooky connections.
So, you see this amazing pattern, right? Every single thing about quantum mechanics that seemed like a problem, a paradox, or just plain weird to Einstein has turned out to be an incredible resource. The spooky action at a distance is now our blueprint for secure networks. The weirdness of measurement is the power behind quantum computing. The paradox became a powerhouse.
This whole journey, from a thought experiment to tech that is literally changing the world, leaves us with one last big question. Proving entanglement was real didn't just confirm a theory. It showed us that reality is way deeper, stranger, and more connected than we ever thought. So you have to wonder, what other impossible things are just waiting to become tomorrow's technology? We'd like to again give a huge thank you to Jörg O. Schneepatt. This entire deep dive was based on his comprehensive essay, which translates to The EPR Paradox, the Riddle of Quantum Entanglement. His fantastic work really let us follow this incredible story from its philosophical beginnings right up to today.
Thank you so much for joining us on this exploration of one of physics' greatest riddles. For more information and to check out the original essay, you can visit schneepatt.de. Goodbye.
Schneepatt.de is a private project by Jörg O. Schneepatt dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.